demand management, so which is the capability to receive and respond to external signals by adjusting real-time energy consumptions. And this requires, for sure, smart meters, intelligent energy management systems, and even smart loads. So you have first distributed generation, the second demand management, and the third storage systems, which is the capability to import, store, and export energy to the grid. And that can be used using batteries, electric vehicles. So you have vehicle to grid and other types of technologies as well. So here in this figure basically illustrates these DER agents. So you have DG, demand management and storage systems provided with these capabilities with energy management systems, smart meters, smart loads, and they are in these smart grid environments. Okay, so they have capabilities that can transform the grid where they are located. When we see the retail electricity market in recent years, some of the things that we can see is number one. So we have retail choice programs in some states. So those programs allow customers to choose not just suppliers, but services according to their preferences. So for example, I'm going to show you a illustration for the state of Texas, for example. If you are located in Dallas, Texas, you can choose your electricity supplier, but not just the supplier. You can choose the service and the amount of renewable energy that you can purchase. For example, if you want at least 60% of your energy being provided from renewable sources, you can have that option. So when you, for example, I'm going to show later, but if you, for example, go to that Power to Choose website, you can type your zip code, and the website will give you a lot of options in terms of providers, in terms of services, in terms of renewable energy options. So you have a lot of flexibility to choose from suppliers and services. The second thing that we observe is that cost reduction of distributed generation boosted net metering programs. So in the US, more than 40 states adopted compensation programs for DG. Okay, not just talking about net metering, but there are other types of incentives and compensation programs for DG. And the number, if we see the number of net meter customers in 2005, it was about 22,000 in the US. And in 2020, this number is more than 2.5 million. Okay, so this is just net metering programs. So, but we have other types of compensation mechanisms as well. And another item that is that we see in the recent retail electricity market transformation is the integration of demand response programs. So those programs allow you to, for example, interact with system operator. For example, if there's a requirement in terms of security for you to during a very hot summer day to increase a little bit the temperature of your thermostat, you can do that in certain jurisdictions. So you can participate, if you don't have any distributed generation, you can participate with your demand, okay? So that's the demand side participation. So when we see the retail electricity market in recent years, one of the key things is the decreasing cost of distributed generation. So here is a chart from NREL where you can see the falling costs of residential PV, commercial PV, and two types of utility scale PV. Okay, one with fixed tilt and the other one with one axis tracker. So you can see that from the last 10 years. So for example, let's see the residential PV cost. In 2010, it was about $7.5 per watt. And now in 2020, it is less than 3, so it's about 2.7. The same trend with commercial rooftop PV systems. And if you see the utility scale PV, the cost reduction is, it's more aggressive. So that includes soft costs, labor, hardware, inverter costs, module, and so on. So we have seen an significant decrease of DG, but in this case PV costs in the last 10 years, and that is another incentive for retail customers to invest in distributed generation, because they are they see, for example, that the payback times will be lower, and they can see that they can contribute for this sustainable trend with their own generation and load. So this is that example from Texas. So if you go to the Power to Choose website, you can just inform your zip code, and this website will give you several options in terms of providers, in terms of services, and as I mentioned before, you can select the percentage of renewable energy that you can purchase from the grid. So you have a lot of flexibility. Okay, so one of the main agents in this retail electricity market transformation include electricity retailers. So they are important agents in the electricity market, especially in the liberalized retail electricity market. So an electricity retailer is a market agent that do not necessarily own any generation assets. Okay, so there are some retailers are purely, investors. Okay, so they can purchase electricity from bilateral contracts, from the wholesale market, or in some cases they have self-production of energy, and they sell energy to retail customers, or they can sell back energy to the wholesale market. So they basically purchase electricity from different types of, they have options in terms of contracts, in terms of wholesale market, or even self-production, and they sell these energy to retail customers, and they can sell back to the wholesale market, right? So they are very important agents in this transformation of the retail electricity market. Another type of agent that this is something that is under discussion, so there's a lot of discussion on this topic, is the distribution system operator. Okay, so right now, this concept, the same term is used in Europe, but here, what I'm presenting here is a little bit different than the term that is used in Europe. So the current discussion on the DSOs is maybe in the future we will need an entity that is able to coordinate, grid operations and facilitate the integration of distributed energy resources. So the same idea of a ISO or RTO and the wholesale market in the transmission grid. So the idea is to bring, this entity to the distribution grid. And we basically have two types of DSO that can be implemented. The first one is called the utility DSO or UDSO. So the DER markets in this framework are operated by, load serving entities such as distribution companies and retailers. So we are considering that the utility DSO does not include an independent entity to operate the market and the grid. So it's the utility itself that will, perform these operations. However, in this type of construct, we need a firewall separation between the DSO block. What I mean by DSO block, I mean network operation and neutral distribution system market facilitation, and the merchant block. For example, if a utility company has investments in distribution generation or other types of DERs, we need this firewall separation, from the DSO block and the merchant block in order to avoid any type of conflict of interests or market power or something like that. On the other side, we have another type of construct, DSO construct, And this is very similar to what we have in the transmission grid or the wholesale market, which is independent DSO or IDSO. So they are basically operated by independent entities, similar to what we have in the wholesale market. But the distribution network assets are still owned by the distribution companies. Okay, so this independent DSO is not responsible for, upgrading the system or maintaining the distribution grid assets. So this is the responsibility of the utility company. Okay, so those are the two DSOs that are, under discussion. So there's a lot of good material about, advantages and disadvantages of each one of these constructs. And so in this paper, I talk about different types of DSOs and how, they can be integrated in the grid. And so in this paper, I also talk about, the current literature on DSO. So there's a lot of models that were developed in trying to integrate these two types of DSOs in terms of economic dispatch, market clearing mechanisms, and so on. So in this paper, we talk about the efforts, the current studies on UDSOs and IDSO. So when we see this power system transformation and the retail electricity market transformation, we see some key elements. So we see new market participants, the integration of multiple demand responsive loads, integration of renewable and distributed generation units. We also see a lot of challenges. So the first challenge is how to coordinate, technical and economic operations in the retail level. So we have a lot of new agents. So how can we make sure, we can effectively coordinate all the technical and economic operations and the distribution grid? Another challenge is to consider the uncertainty on high penetration of distributed renewable energy. So as I mentioned before, we have the widespread adoption of distributed solar and electric vehicles. So how to consider this high number of new and small scale agents in the distribution grid. So we definitely need new visions, frameworks, and roadmaps for integrating DER in the retail market. Okay, and we need new market mechanisms and decision-making models to accommodate DER. So the current, trading mechanisms for DER that we have in place right now, they are not, adequate to accommodate a large number of future distributed energy resources that will be integrated into the grid. So net metering is not the solution. We see the example in California. So we need to design a new mechanism or new types of mechanisms that will facilitate the integration of DER, and at the same time will make sure the technical and economic operations are effective, for each agent, for the system operator, that will satisfy the power system constraints and so on. So that's a huge challenge that we have ahead. So this is one of the things that we worked in the last year. So I worked on developing a high-level vision and framework of the next generation retail electricity market, especially in the context of DER. So as we see this trend, this transformation, we basically see that we will need 5 key things in the next generation retail electricity market. So number 1 is operation optimization. So we need accurate, cost-effective, and timely decisions, reliable transactions and grid operations, efficient integration with wholesale markets. So this is very important, not just looking at the retail market, but how to integrate retail and wholesale markets, and the DER value in each node. So for example, we know that at different times, the energy that you export to the grid should be valued differently. For example, if the grid is under any emergency condition, the value of the resource that you provide to the grid is higher than if you are just exporting at under high solar energy production in the whole system, right? Another key thing is flexibility. And that includes the integration of new technologies, new market agents. So we are talking about increasing the host capacity of the system, and also the capacity to deal with uncertainties and the utilization of local resources. So if I have a certain emergency condition or anything that I need to address, how can I use my local resources to address the issue, instead of always depending on centralized generation units and transmission lines. So another thing is customer integration. So we will need fast, friendly, and efficient interaction platforms for market agents' convenience in order to increase the social engagement and the social welfare maximization. So for example, the situation that happened in Texas about 2 weeks ago. So there's a lot of discussion on, we need to be independent from the grid, so we don't need the grid because we don't want to be, without power for days or for weeks. So there's a lot of discussion, on customers thinking about, having their own system and being independent from the grid. So if we look at the next generation retail electricity market, if we want a really efficient and effective market, we need to develop fast, friendly, and efficient mechanisms, to make sure we have social engagement. So then we can use the local resources to, provide benefits, not just to the local system, but maybe we can use the local resources to help other regions, other states, other jurisdictions, okay? And the last key thing is the sustainability for sure. So the maximum integration of clean and renewable energy resources, energy efficiency initiatives, that's very important, and incentives for the adoption, okay? But in order to have these key, things being implemented, there's a lot of needs, okay? So we're gonna need new business models, so grid infrastructure and operations. We're gonna need innovative DER technologies, and we also have to think about distributed grid services. So for example, how DER agents can help with congestion and losses management. How can we implement, for example, ancillary services market in the distribution grid, and how we can implement better demand management strategies, okay? So another important thing is the integration of retail and wholesale market, right? So in this vision, we basically have a lot of new types of information and power flow. So for example, we need new types of information flow. So as a active retail customer or active DER agent, we need to have better interaction with our system operators, with our communities, with our neighbors. So it's very important to design a framework that allow us as end users, retail customers, to have the opportunity to interact with system operator, not just in terms of providing energy to the grid, but also seeing what is the condition of the grid in real time. So how can we, how can I help, or how can I provide benefits to the grid, with my local resource? So we are gonna need a better integration of wholesale market and retail market, in terms of energy, but also information flow. And that, especially this new flow of information, we have a lot of issues and concerns related to our communication infrastructure, related to cybersecurity. So we need to develop new mechanisms that are secure and that are easy to implement and that are friendly and that do not have any problems in terms of transmission delays and so on. So we have to consider not just these aspects, but also a lot of other aspects that are very important for the implementation of this. Okay. So here I basically show that the roles and responsibilities of some retail market agents might change in the future. So especially if we have the implementation of DSOs. Okay, so they will be responsible for operating the retail market in an efficient way. And DSOs here can be the IDSO or the UDSO that I mentioned before. So their role will be making sure that the market and the grid operations are effective, and that the integration between retail and wholesale is effective as well. So they will need to develop planning, scheduling, and settlement markets for DER in order to use the local resources to benefit the whole system. And here are some capabilities of comprehensive DSO. So this is, for example, if you consider a DSO that has a lot of different capabilities. So this is a picture of a comprehensive DSO. This is something that we are far away from achieving right now, having a DSO that is able to perform or coordinate ancillary services market in distribution grid, distribution expansion planning, forecasting planning, integration of DR, social welfare maximization in the retail market, market integrity and transparency in the retail market. So these are some of the functions that comprehensive DSOs will need to have in order to be, effective operators in the future retail market. So here I'm going to show you work that we developed about 1 or 2 years ago. For example, when we see the current retail electricity market, distributed renewable energy is not considered a competitive resource. Okay, so we have competitive retail electricity markets in terms of energy. Okay, so you can choose different suppliers and services, but as a producer of renewable energy, small scale renewable energy, you don't have the option to choose your, to who you are selling your energy. Okay, so DG producers, if you don't participate in the wholesale market, okay, if you're a small scale DG producer, you do not have the option to choose, the buyer of your distributed generation. Okay, so this is something that we analyzed, and when we see this vision of the retail electricity market, we see that competition, flexibility, and customer integration are key things. Okay, so when we see the existing literature in the DG trading in the retail market, we don't see distributed renewable energies as a competitive and liberalized resource in the market. Okay, but we know that the liberalized DRE market can help several agents, and avoid high price fluctuations in the wholesale market. For example, if you are an aggregator or retailer and you can have the option to purchase the distributed renewable energy from different types of producers, that might help you to avoid the risks in the wholesale market. Okay, and if we have a liberalized DRE market, we make these small scale DG producers more active in the electricity market. So remember that those small scale DRE agents, they do not have the option to participate in the wholesale market. Especially here in the US, you have to have a certain capacity in order to be eligible to participate in the wholesale market. So if you're still in the retail market, you don't have many options in terms of, for who you can sell your power. So this is a study that we developed, liberalized DRE market. Okay, so for example, consider a DRE producer, a small scale DRE producer in a local distribution grid. Okay, and this DRE producer can sell its renewable energy to a lot of different, participants. for example, in this case, we are considering a electricity retailer, okay, that we're going to study. And this DRE producer can sell energy to a lot of other agents in the market. For example, you have other retailers, you have aggregators, you have, different options. So here we are dividing the agents of the market, basically the retailer that we're going to study, and a lot of other competitors. So here we are calling rival market agents, okay? So those are the competitors of these retailers. So the retailer under study and all the other competitors will, compete for buying DRE from a group of local DRE producers, okay? So the objective here is to model the interaction between the retailer, the rivals, and a group of DRE producers, okay? So we can basically model this decision-making strategy by using bi-level optimization, okay? So for example, consider that you have an electricity retailer in the upper level, okay? So this electricity retailer has to decide, for example, the day-ahead market purchases and the DRE price bids to this liberalized DRE market, okay? And on the lower level, you have a group of DRE producers, okay? So, and these DRE producers will receive a lot of price bids. One bid from the retailer that we are studying, and the other price bids from the competitors or the rival market agents, okay? So we can model different types of decisions here. In the upper level, we have the electricity retailer. And as I mentioned before, what are the decisions of this electricity retailer? The day-ahead market purchases, the price bids for DER, and there's a lot of uncertainties to be considered here. One sort of uncertainty is the power demand, DRE production, day-ahead and real-time market prices, and so on. In the second stage, we have the real-time market. And again, here in the second stage, we are assuming that all the uncertainties are not uncertain anymore. So the retailer has knowledge on all these variables here. And in the lower level, the DRE producers will basically receive a lot of bids, and they will decide the percentage of DER to be sold to each participant, okay? Maybe it's going to be 20% for our retailer and 80% for the rest. Maybe it's going to be 100% for our retailer and 0% for the rest. So we don't know. Why is it a bi-level program? Because the price bid of this retailer will depend on the decision, of the DRE producers on the lower level. So that's why we have this bi-level framework. So this is the mathematical formulation that we developed. In the first stage, the objective is to minimize the procurement cost of the retailer, okay? And the constraints that we have power balance constraints. Here, we are assuming that the retailer wants to buy a minimum amount of DER from the market, okay, for a certain scenario. The other constraints include the power bidding in the wholesale market and the risk management. So here we are considering a conditional value at risk to model the risk management of this retailer. And in the lower level, we have the expected revenue of the group of DRE producers, and these are the buyer selection constraints. So basically, the DRE producers, they have to determine a certain percentage of the share of DRE they are going to be selling to. So this program is nonlinear, it's bi-level, so it cannot be easily solved by commercial solvers. So in order to convert this problem into a single level mixed integer linear program, we have to use the KKT conditions in the lower level. And basically we use, we replace some linear expressions by nonlinear expressions by linear expressions using complementary slackness, and also duality theory to replace these bilinear products by linear expressions. So our final problem is a single level mixed integer linear programming that can be solved by any existing solver. So this is the resulting linear single level problem. And note that we have one constraint that basically specifies a minimum amount of DRE that this retailer wants to buy from the market. For example, and here there is a requirement, phi. So this variable basically sets, I want to purchase 70% of the available DRE in the market. So in this case, the retailer can specify a certain amount of energy to be purchased from this DRE market, okay? So in our case studies, we consider a retailer in the PJM market, okay? A group of commercial scale PV producers with a total capacity of about 200 megawatts that are assumed to participate in this market. The rival market prices are randomly generated, okay? And the uncertainties associated with PV production are based on historical data from NREL. And the uncertainties associated with the retailer's client and the wholesale market prices are generated from the PJM historical data. So we basically collect historical data from day-ahead market prices, real-time market prices, solar energy, and electricity demand. So the solar energy production from NREL and all the other data from PJM. So we use a seasonal autoregressive integrated moving average model to generate scenarios. So we came up with 500 scenarios for each uncertain variable. However, the number of scenarios here is too high. So in order for the model to be, easy to optimize the system in acceptable time, we have to do some scenario reduction. So we use the fast forward scenario reduction algorithm to reduce the number of scenarios from 500 to 4, 4, 4, and 3. So the demand scenarios is 3 here because the data set is less variable. So the standard deviation of the given data is lower than the other variables. So we could reduce the final number of scenarios to 3. So the total number of scenarios, considering the scenario reduction, is 192. So if you multiply 4 times 4 times 4 times 3, we get 192 scenarios. So here are some results. So we basically consider 2 scenarios or 2 cases. The first case assumed that the price bids of the rival market agents, they have the expected value near the same and the standard deviation lower than those of the real-time market prices in every time period. So in this case, what is the meaning of this statement? The electricity retailer has the option to purchase energy from the day-ahead market, from the real-time market, and from this liberalized DRE market, okay? So this case 1 basically means that the prices of the rival market agents, they have the expected value is about the same of the real-time market, but the standard deviation is lower, which means that the prices are less variable than the real-time market price, okay? So in this case, we don't need to set a minimum amount for DRE purchases, okay? Because the expected value is nearly the same of the real-time market, but it's less variable. So of course, we don't need to set a minimum DRE purchases because the model will automatically, consider this DRE market, all right? So here I show the expected values and the standard deviations of the day-ahead, real-time, and the rival market scenario. So, and this table was generated to consider randomly, okay? So in this case, the expected cost of the retailer participated in only the wholesale market and participated in the wholesale market, and this liberalized DRE market was compared. So you can see that for the hours where we have solar energy production, the cost of the retailer in participating in the wholesale and the DRE market is lower than the cost of just participating in the wholesale market. So here we basically analyze the cost reduction of the retailer participating in this liberalized DRE market, okay? Here is the impact of the risk management. So you can see that if beta, which is our risk aversion level, is 0, that means that the retailer is willing to take risk, okay? So the expected cost of the retailer will be about 1.98 to the 10 to the power 5. But as we increase the value of beta, or as we increase our risk aversion, the expected cost of the retailer is higher, okay? But the conditional value at risk is lower. That means that the scenarios where you have a lot of losses, okay, you're gonna basically eliminate some of those scenarios. So you take less risk, but you also increase your expected cost, okay? And here we also show the impact of different risk aversion levels on the day-ahead bid capacity of the retailer and the wholesale market, and also the price bid of this retailer, okay, in terms of DER. So the more averse is the risk, is the retailer, the DRE prices will be higher, okay? And why is that? Because as I mentioned before, the DRE market has less variability. The standard deviation is lower than the standard deviation of the real-time market. So that's why for a very risk-averse retailer, this retailer wants to purchase more power from this liberalized DRE market. The other case assume that the rival market agents' price bids have a higher expected value and a standard deviation lower than those of the real-time market prices. So that means that the model, if you do not specify a minimal amount of purchases from this DRE market, the model will not buy anything, because in this case, the expected value of rival market agents is higher than the real-time market prices. So we have to set us, we have to specify a minimal amount of DRE purchases. And again, here we show the expected values and the standard deviations of day-ahead, real-time, and rival market agent prices for the hours with solar energy production. And this table was generated randomly again, but now we have a standard deviation that is higher. So here we see, on the left-hand side, the impact of phi. So as we increase the value at phi, okay, for example, if phi is 0.25, okay, we can see that the price offered by the retailer is lower, okay? As you increase the value of phi, so if you go from 0.25 to 1, the DRE price offered by the retailer is higher. And that makes sense, because if you want to purchase more energy from DER, your price bid has to be higher than your competitors, right? Okay, and this is the impact of phi in terms of day-ahead bid capacity, okay? So as you decrease the value of phi, you basically buy less power from the day-ahead market because you are purchasing more power from the DRE. And this is the impact of risk management, considering different values of phi and different values of beta. So you can see that's very interesting, because you can see that if your retailer is, very risk averse, the expected cost will be very high. So in this case, we are analyzing different values of phi, okay, and different values of beta. Okay, so if phi is 0, okay, that means that you don't want to, purchase a specified number of DER from the market, okay? So your CVR variation will be higher and your total expected cost will be lower. However, if you specify a very high amount of DER purchases from this DRE market, your expected cost will be higher and your CVR variation will be lower. Okay, so here we see that this DRE market can also help the retailer to reduce the risks in this power trading. Okay, it's another risk mechanism, risk management mechanism, in addition to the CVR that we are considering here. So this model, we basically developed a short-term decision-making model for an electricity retailer, considering a liberalized DRE market. Okay, the resulting model is a mixed integer linear problem that can be efficiently solved by commercial solvers. And the simulation results have shown that the retailer could reduce its expected cost participating in this market. Okay, so this market is an alternative to the wholesale market, for example. So we showed that participating in both the wholesale market and this liberalized DRE market, the retailer can reduce costs. Okay, so it's not meant to replace the wholesale market, but this is in order to complement the wholesale market. So in both cases, the proposed model provides the optimal decisions for the retailer under different risk aversion levels. So we basically show two cases. One where the expected values of the rival market agents were higher and lower standard deviation. And in case two, the expected values were higher with lower standard deviations. And in both cases, the model can provide the optimal decisions for the retailer. Some future research directions include considering other types of uncertainty modeling. So in this model, we use stochastic optimization. However, you have to consider a lot of different scenarios, right? And for example, in this case, we model the scenarios for rival market agents generating, those scenarios were generated randomly, okay? However, we need to investigate, for example, other types of uncertainty modeling, okay? So we are working on considering a robust optimization version of this problem. So we don't have to model scenarios for rival market agents, especially because we don't have data right now. So I think a robust optimization is a good alternative to model these type of uncertainties without having to depend on scenarios. We can also study the decision-making strategy of a single rival market agent or a group of rival market agents under this proposed liberalized market. Another thing that can be included is storage energy systems. So how including energy storage, how it will affect the decision model of the DRE producers in the retail electricity market, okay? And another important thing is to understand the impacts of these type of liberalized DRE markets on power grid, on distribution grid, power flow, node voltages, losses. So, a key challenge is studying not just the economic impact, but also the technical impact. So how this can affect, power flows, the voltages, the losses of the system. So this is a future work that might be very interesting. All right, so that's it. Thank you so much for your time, and I'm happy to answer any questions that you might have.
Yeah, thank you. I think there are 2 or 3 questions in the chat. And you see it?
Oh, yeah, I can see it. First question, what are the information flowing from DSO block to front merchant block, actually? Okay, so you're talking about the separation between the merchant block and the DSO block. That's not very clear. How can we get this firewall separation? So there's a lot of studies, proposing some regulatory mechanisms to separate the merchant block and the technical block of a DSO. So that's a interesting effort. So I have seen a lot of papers, a lot of not just papers from academia, but a lot of proposals from regulators discussing some options to separate this, these two blocks. Okay, so that's why people tend to accept more the independent DSO than the utility DSO. Another question: how do we get visibility of DER for integration into the market? DER at what voltage level are feasible? So yeah, that's a great question. So visibility is key, in order to provide, in order to design markets that are can provide benefits to the system. So one of the things that we are considering here, another study that we recently developed was to model a distribution system market clearing, okay, and settlement mechanism. So one of the assumptions that we have to make is that DSOs, they have visibility, okay? So if you are a small scale renewable energy producer, the DSO knows, how much you are generating, and, so the DSO has this visibility, and we here assuming that smart grid technologies or innovative smart grid technologies can be integrated, in this relationship. So we are basically considering that communication capabilities will be increased, the system transactions will be safe and secure, okay? So we don't have any problems in terms of communication delays and so on. So when we model a system, a distribution system market clearing or any type of interaction between DSOs and retail market agents, we are assuming that visibility is a key, is addressed here, okay? But we understand that it might take some time in order for us to have, the visibility thing, completely addressed. So we are assuming that DSOs have, entire visibility of what's going on.
Thank you. Yeah. And I think the other was the voltage level. So what feasible level you think that maybe a 13 kV DR will have visibility, or even you go all the way till secondary network?
That's something that we didn't model, but that's a great question. That's a great question that I don't have an answer for that, but this is something that we can definitely, for example, we are working on integrating these market mechanisms and considering more grid constraints and more. So this is something that we can actually do is, test the impact on the grid for different voltage levels, So for that, we need different types of test cases, and that's a great future work that we can develop. That's a great question. I don't have the answer right now, but for sure we need some studies,
Yeah, I think, I mean, these are challenging, and everyone is kind of thinking about that, how to balance between higher visibility and engaging those resources and complexity that will increase with that.
Yeah, definitely.
Okay, well, and any other question from anyone else? So we're right on time. We just have 1 minute left. I don't see any. So thank you so much for doing it. I think it was just one popped up. It is. Maybe you can see the question. So
yeah, sure. So it's well believed that economies of scale could significantly reduce cost of PV batteries, but the cost of generation from conventions won't decrease that much, especially where the majority of the cost is variable. Yeah. Yeah, that's right. So here we're considering that the cost of renewable, distributed generation will decrease, and there is not just the mindset of reducing costs, but also increasing the sustainability. So even if DG is not the most viable option, even if renewable distributed generation is not the most cost efficient option, we are assuming that the next generation retail electricity market will have the emphasis on sustainability. Okay, so we see a lot of examples where people invest in DG in states where the payback is not the best, but they have this mindset of sustainability. So this is also driving adoption of DG, even if it's not the most cost-effective option, But you're right.
All right. Well, so thank you so much. I think it went very well, and look forward to further interaction later.
Yeah, thank you so much. Thanks for having me today.
All right. Thanks everyone for joining. Have a great day. Bye.